Although Albert Einstein was seen as one of the greatest minds of all time, even a mind as great as his was unable to come fully to terms with the ideas of quantum mechanics. He was quoted to say that God does not play dice. He spent 3 or 4 years afterwards trying time and time again to prove quantum mechanics wrong. When he was finally proven wrong for the last time, he finally said that quantum mechanics could not be the final theory. More than 100 years later, quantum mechanics is still the best explanation we have for modern-day physics. To understand quantum mechanics, first we have to understand two things. Those two things are that all units in energy are quantized. What does quantized mean? Quantized just means that it comes in a small packet that can't be made any smaller. These packets are called Planck units. So what this says is that you can only give energy to something in a certain amount of Planck units, and you can't cut these into any smaller units than that. The other part that we have to come to terms with is that particles can no longer be seen as particles. They must be seen as waves. Back in classical mechanics, we see particles as these solid balls that can travel in directions and collide with each other. But quantum mechanics says that this is not true. Instead, we have to think of particles as waves. And when these waves propagate through space, we only have a chance of seeing where they are and where they'll collide, and where these propagations cross over with each other. So at all of these spots, you have an opportunity of these particles or waves colliding with each other. How do I make this seem a little more concrete? There's an experiment that's known as the double slit experiment. First, we have a firing device that we'll call a particle accelerator. We have a plate with a slit in the middle, and we have a photosensitive piece of paper behind it that just registers with a dot whenever any sort of light strikes it. Now, if particles reacted as balls, or reacted like balls, we would expect that when they are fired out, we would see a pattern in a straight line in the same shape of the slit. And if we were to add a second slit to fire through, then these particles should make two straight lines as they're fired through. But the thing with quantum mechanics is that this is not what happens. Instead, when we fire through one slit, we have a very strong and bright sequence in the center, and then random scatterings as it goes out. And if we add in a second slit, then instead of the two solid bars, we actually get sequences of interference in between where the particles collide with a photosensitive paper. Like so. What this means is that instead of as a solid ball, when the particles travel through, they actually come through as a wave. And when they come through as a wave, these waves cross over, and these spots where they interfere cause these blank dead zones in between. And the weirdest part about this is that the particle doesn't travel through either one slit or the other. It actually travels through both. And this was tested when scientists thought that there's no way that this could be true, that they put a little sensor on top of each of the slits. Say these little blocks are sensors. So now we could measure which slit that each of these particles went through. But what happened when we tried to measure which one they went through, here's the interference, here's the pattern that we saw. Which is exactly what would happen if we were firing solid balls through the slits at the screen. So when observed, particles will act as solid balls, but when not observed, particles will act as waves. To make things even stranger, particles can be what we call entangled. What this means is that if I was to fire out a particle beam, we'll call it as a normal laser, and I fire this out to hit a mirror that would split this beam in two different directions. This direction and this direction. And we have a sensitive photogate at each side. If I was to make a measurement of this beam from one of these particles, so let's say the angular momentum of either up or down, whenever I make this measurement, the opposite side immediately turns towards that direction. And this experiment has been done over gaps of over a mile. So there is no set distance that this happens. Einstein referred to this as spooky action at a distance. So what's actually happening is somehow these particles are, although they're not communicating, they're able to synchronize as soon as one of them is measured. So given these few crazy ideas that we've just discussed, we've actually, over the last 100 years, been able to come up with computers, cell phones, TVs, and many of the things that we use throughout our day-to-day. So next time you're sitting there with your friends and you're all sitting there bored, you can say, "Do you want to hear something crazy?"